Hi, I'm Ryan Nicol, CTO at DSA Ocean, and today I want to talk about some of the nuances and details of the hydrodynamic fin stabilizer model in the ProteusDS ShipMo3D toolset. It's important to get an appreciation of these details so that you have an understanding of the implications when you're using them in ship motion assessment, both in ShipMo3D and also in the Ship Motion toolset when you're doing a comfort analysis. So I have the 50-meter generic yacht set up here with some fin stabilizers. You can see the appendages in red there, roughly midships. And first off, I guess the most important thing to do is just summarize what it's actually doing. This is resolving the lift force on these stabilizers as a function of angle of attack and forward speed. So this creates a hydrodynamic force that's going to, apply forces to the ship and affect the ship motion in the seakeeping and also the time domain seakeeping maneuvering analysis in the ShipMo3D toolset. It's also going to affect the motion RAO calculations, which then go and get used in other calculations like in the Ship Motion toolbox and so on. So we'll talk a little bit more about what all those implications are and what else it's doing. But one thing I want to highlight first is some of the limitations. So this control mode is purely sinusoidal actuation, and what that means is that in some cases with commonly available fin stabilizer equipments that work at zero speed, they use a completely different kind of control methodology. They actuate them more like in a paddling motion that uses a different approach and to create the hydrodynamic forces to slow down the roll motion of the ship. So you'll see these in, for example, well-known companies like Quantum Stabilizers, and you can see a bunch of different kinds of fin designs they have, and there's lots of other equipment suppliers, well-known suppliers like hydrodynamics as well, and others like CMC Marine and SKF and so on. Many of these have zero speed capability as well as, or at rest, they refer to them at different terminologies as a different kind of control mode when the ship is sitting still, is not moving forward. So that control methodology is not included in the fin stabilizer model. That doesn't mean that there isn't a way to incorporate the effect. You can do and make an allowance for that by applying an external roll damping factor here, but that's out of scope of this video, and there's a different process for that. So the other thing that's important to know is the input parameters. They give you a control over the span, the chord at the root, and the chord at the tip. So you can put in, there's a relatively limited range of geometries you can put in. As you can see with many different commonly available fin stabilizers, they have a little bit more of a bit of a more complex shape to them. So you have to make some kind of approximations here and there. And another important limitation is there's no functionality for accounting for things like end plates, like you'll see on the CMC fin stabilizers here. And then when you look at SKF fin stabilizers, you'll see these anti-vortex vanes on the tips as well as flaps. So flaps and tip effects, those are not accounted for in the hydrodynamic model. So it's important to understand those limitations. They'll have little details and little differences, but still in the context of early stage design, it's a great way to capture some of the effects of these hydrodynamic appendages on the system. So let's focus and turn the conversation around a little bit more about what it is doing and how does it help. So in the seakeeping calculations, seakeep regular and seakeep random, these are all frequency domains, so everything is sinusoidal, everything's linearized, but the forces are highly nonlinear. So what's happening behind the scenes is an equivalent damping coefficient is resolved in an iterative process in the solution process for solving the system equations of the ship dynamics. And it's incorporating the wave height and the resulting motion of the ship and normalizing the roll damping from an equivalent power dissipation. So the implication of this is that you do get a damping effect from the fin stabilizers that changes with wave height. And it's a really robust way to capture the hydrodynamics of these kind of nonlinear appendages. And as it's a full 3D formulation, you're getting the effects of what the fin stabilizers are doing, no matter where they're placed on the ship, and then also the relative sea direction as well. And again, it's a forward speed code, so the intensity of the speed is also having a strong impact on what the fin stabilizers are doing. So you can see this is an output from Seekeep Random showing the generic yacht motion affected by the fin stabilizers across a wide range of different wave directions. So the last thing I would just highlight again, at zero speed in this software, in what the code is going to be doing, because the lift forces are proportional to the forward speed, they won't be doing anything. However, there is still a passive damping effect that it will have. And what I mean by that is the fact that there are these plates here. Yes, there won't be a lift force from them, but there is a damping normal force on these fins, so it will start to make a small effect, especially compared to the bare hull. The other thing to keep in mind is that there will be a coupling effect to other degrees of freedom, so if these fins are placed, say, more towards the bow of the ship, that'll start to affect pitch motion as well. So really what I wanted to do is just give a basis for what's happening in the behind the scenes in the hydrodynamics for the fin stabilizer model, to give an initial appreciation of what the implications are of using them. It's meant as a starting point for using this kind of functionality, which I think will give you a lot of insight into what's possible, especially at the earliest stages of design. Of course, it makes there's many reasons to consult with equipment suppliers on how they can help establish a robust design, but a tool like ProteusDS here gives you some idea of how things might behave when there's so much conceptual design going on and rapid changes in design at the early stages. So thanks for watching.